Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'll show CFD analysis of a U-shaped heat pipe using SolidWorks flow simulation. This is actually a different type of analysis. In this analysis, we'll try to provide better cooling with fins and by the help of sufficient amount of air. Mainly we consider this heat pipe analysis as an internal analysis, but in this case we'll consider this one as external analysis because our aim should be to minimize the temperature of the condenser zone, and that's why we have provided some fins, and from outside we'll be providing air at a specific rate. Okay, so you can see the model. This is the heat pipe, and down you can see this is the heat source. And if you see from this side, the fins are actually having some support from the bottom, and this is not a continuous object. The bottom is only a support and the fins are actually separated from that bottom surface, right? So the fins will be providing cooling for that condenser zone, and from backside we'll be providing air at a specific rate. And if you see the heat pipe, the bottom part is known as the evaporative zone. This is the adiabatic zone, and the top part is known as condenser zone. This model has already been made using SolidWorks. Now we'll go for simulation, and the simulation environment will be initiated with the wizard itself. So let us start from wizard. Default name of the project we are keeping as project 4. Next to that, you have to select that unit system, and we are considering SI unit system as usual. Pressure we'll consider as bar, and temperature will be degrees Celsius. Next to that, we have to select this one as an external analysis. We can consider this one internal also, but our aim is something else. Our aim is to provide huge amount of cooling with air, and air will be flowing at a specific velocity from backside, and our main aim is to provide sufficient amount of cooling at the condenser zone. So we're considering this one as an external analysis. From physical features, it will be heat conduction in solids, and definitely gravity will be involved, as heated air has a tendency to go up, and the direction of gravity will be y. Along y it will be minus 9.81 meter per second square, and along z direction it will be 0. Next to that, we have to select gases and fluid. Default liquid will be water inside this heat pipe, and that will be kept at a very low pressure of 0.4 bar. So we're considering default fluid as water, and for cooling we'll be providing air at a specific velocity from backside. Next to that, you have to select materials. Default metal for the heat pipe will be definitely copper, and other materials will be provided during application of boundary conditions. Next to that, roughness parameter we are considering as default, and thermal parameters, let us consider temperature to be 30 degrees centigrade. Let us consider temperature to be 30 degrees centigrade, and solid parameters, definitely it will be also 30 degrees centigrade, and atmospheric pressure will be 1.01325 bar. Let us finish this. You can see the computational domain is ready. So this is the domain. We have to minimize this domain because higher the volume of the domain, larger will be the time for calculations or iterations. So let us make the domain as small as possible. So let us edit this part. Let us edit this from side view also. Green check, it is done. Next to that, we can see it from front side, and we can hide this computational domain for providing our boundary conditions and other necessary initial conditions. Right, this is our model. Next to that, we have to select the fluid subdomain, because inside this heat pipe we'll be providing water at a low pressure. So fluid subdomains, insert fluid subdomain, going to provide water at a pressure of 0.4 bar and temperature will be 30 degrees centigrade. You can select that domain, select other, you can select the face of sweep. So this is the computational domain for heat pipe, and inside this one very little amount of water will be flowing. Again check. Next to that, we will select solid materials, insert solid materials, predefined. Initially we will select copper for this heat pipe, so we can select it from metals, copper, and the solid metals can be selected from the geometry itself. Let us select that evaporative part, the adiabatic section, and also the condenser zone. So this is the whole heat pipe, and the material for this heat pipe is selected as copper. Done. Next to that, we have to provide other materials. You can see bottom part we have provided one heat source that will be made up of titanium. So we can select material from here, insert solid material, predefined metals, and we want to provide titanium for the heat source. Selected, green check. Next to that, we have to provide that fins and the base support as aluminum. Solid materials, insert solid material, predefined, it will be aluminum 6061 alloys. Select that alloy. We are selecting that material, the base, the support for these fins. Now we can select the fins from the geometry itself. Select, all the fins are being selected. Done. Green check. So we have provided aluminum 6061 for the fins and the base support. Materials have been provided. Next to that, we have to provide the heat source. We can provide it from conditions. For providing heat source, let us make some part to be hidden, right? Let us make that evaporative part to be hidden. Done. Now we can provide heat source for these surfaces. Condition, surface source. Let us select the surface. This is the bottom surface, this is the top surface, and also other surfaces needed. From this side also we can select the other surface. So from these three different surfaces, we will be providing heat at a rate of 1 kilowatt or 1000 watt. Green check. Next to that, we have to provide contact resistance in between the two surfaces of heat source and the evaporative zone. It will be obtained from here. Conditions, contact resistance. Then select that surface here. Next to that, we have to select that surface of the evaporative zone that can be taken from the solid geometry. Selected, and it will be predefined, and we have to provide zero contact resistance in between these two. Green check. Done. Next to that, the most important part, that means we have to provide the properties of this heat pipe that can be obtained from here. Conditions, heat pipe. Initially you have to select all the parts of the heat pipe that can be selected from here. Evaporator, adiabatic section, and also the condenser. All the parts of the heat pipe is selected. Next part, you have to select that heating zone or the heat surface. Selected, and finally we have to select that cooling zone, that means the fins. We can select these fins in this way. The fins are being selected. It is done. Next to that, you have to select effective thermal resistance. It is an experimental property. Its value will be 0.01. Green check. Done. Next case, you have to provide some kind of goals, and our aim is to have the temperature of the condenser to be very less. So what can you do is, let us select some goals. Insert surface goals. We want to select average temperature of fluid at different zones of this heat pipe. So it will be average temperature of fluid, and we have to select different zones of heat pipe. From the geometry itself, we will select evaporator, adiabatic section, and also condenser zone, and we want to create separate goals for each of them. Selected. Green check. Goals are made. Now we can rename these things as, this one will be average temperature of fluid at evaporator. Second one will be average temperature of fluid at the adiabatic zone. And the last one is average temperature of fluid at the condenser zone. All the goals are defined. Next to that, we can do one thing else. That means we want to provide airflow from backside. That can be done from general settings. We can go back a little bit and we'll see the initial ambient conditions. From there, we can select that air will be flowing at a velocity of 30 meters per second with some specific direction. Let us seek the direction of air. It can be obtained from here. That means it will be flowing from Z direction, right? You can see the direction of air. It will be flowing along Z. So velocity of air will be 30 meters per second. And we can select the coordinate system as Z. Okay, done. That means from outside, air will be flowing at a rate of 30 meters per second from Z direction. We can finish this. This needs to be created in pre-processing stage itself. Anyway, all the goals have been defined. Next one, we can run this simulation. Let us run it with new calculations. Iterations already been started. Mesh and model preparation is going on. You can see the solver is finished and all our results are converged. And because of sufficient amount of cooling from the air, as we forced air from backside from Z direction with a velocity of 30 meters per second, so we could not see that much of a rise in temperature in the heat pipe. But according to principles of heat pipe, we can see that maximum temperature is obtained in the evaporator zone, which is indicated by red color. Its temperature is 31.2 degrees centigrade. Then we can see the next temperature is in the adiabatic zone. It is 30.125 degrees centigrade, and minimum temperature is at the condenser zone, which is 30.0029 degrees centigrade. That means by providing heater also, we could not achieve that much of temperature because of cooling provided by air. In next analysis, what we'll do is we'll replace the air and see what is the difference. Next analysis, we'll not consider our air supply from Z direction. So what we'll do is we'll edit this one and replace that pre-processing condition. That means from general conditions, we'll replace that initial conditions. Let us neglect this one. That means we are not supplying air from Z direction. And similarly, the coordinate system also we are not considering as Z. It will be as usual X. Okay, done. Let us run this one with the change condition. That means in this case, we are not supplying air from Z direction. Let's see how the results are obtained. Let's run it with new calculations. The solver has already started iterations. It is preparing the model. Mesh refining is going on. We can see our solver is finished and our results can be obtained from the goal plots and different cut plots. Also we can see our results. Like you can see, when we didn't supply any kind of force here from backside, In that case, we could see that huge amount of increase in temperature at the evaporator zone. And as we have provided fins at the condenser zone, in that zone we could not see any kind of increase in temperature. And in the adiabatic section, we could see the temperature is in the mid-range. Color of this adiabatic zone, it is indicating that it is in the range of 35 to 40 degrees centigrade. Okay, let us see our results from the wall ports results, and want to see our results from front plane. Let us view that object from front plane. So cut plots, insert cut plots, and we want to see temperature fluid across front plane. Instead of pressure, we can change it to temperature fluid. Grain check. This is the flow of fluid across front plane. Let us make the object to be transparent. It's completely hidden right now. Now you can see the gold plots from here. Cut plots. Let us show. This is the cut plot along front plane. Now I want to see this in the form of an animation. It is clearly understood that at the evaporative section, the temperature of fluid is high. It is indicated by red color, and in the adiabatic zone it is in the mid range, and in the condenser zone it is very less. You can see these things from right plane also. Let us clear and hide these things. We will see this from right plane. Cut plots, insert. Let's see this thing from right plane. Grain check. Now we can change the orientation of this view. We're going to see from right plane. Let us see the animated view of this one. It is showing that at the bottom part it is red, which is indicated by a temperature of 53 degrees centigrade, and at the top level it is approximately 30 degrees centigrade. Right, you can see this by rotating also. And across the fins, its temperature is indicated by blue zone, that is near about 30 degrees centigrade. Okay, let us clear and hide. Next to that, what we will do is we will change the analysis type. Instead of external one, we will see this one as an internal analysis. That means we want to remove the air and see what is going on inside. We will see inside this heat pipe how much temperature will be developed if there is no cooling by air. So next case, we will change this analysis as an internal one. We can do it from the general settings. It will be an internal analysis, and we have to remove air from the fluids because we want to consider only water inside these heat pipes. So air will not be there. We can remove air. It is only water right now. Now with same conditions, this one will be considering as an internal analysis without supplying any air from outside. Let us see how the results are obtained. Let us run it. With same conditions, we are considering a new calculations. The solver is finished. We can see here when there is no air supply without any cooling, the maximum temperature is in the range of 2700 degrees centigrade and minimum temperature is 2276 degrees centigrade. So you can see here the maximum temperature is in the evaporative zone, and in between these two adiabatic zone, their temperatures will be in the range of 2500 degrees centigrade, and at the condenser zone it will be near about 2400 degrees centigrade, as it is indicated by yellow and green zone. Okay, actually we did three different types of analysis. Let us close these things. In this CFD analysis, we conducted three different types of analysis. Two were external analysis. In between these two, in the first analysis, we forced air from backside with a specific velocity of 30 meters per second. And in that case, we could see that the temperature in evaporator, condenser and the adiabatic zone, there was very less temperature increase. and the temperature in different zones were having a difference of 1 degree centigrade. That means it was having the temperature of 32, 31 and 30 degrees centigrade when we forced air from the backside at a velocity of 30 meter per second. In the second analysis, we also considered that one as an external analysis. In that case, we didn't force air from backside. In that case, we could see the maximum temperature was 50 degrees centigrade, which was obtained at the evaporator zone, and the adiabatic zone was, in that case, it was near about 40 degrees centigrade, and the temperature at the condenser zone, it was near about 32 degrees centigrade. And in the last case, we conducted one internal analysis. In that case, we completely avoided air, so no cooling was there. In that case, we could see the temperature at the evaporator zone was 2700 degrees centigrade, and in the condenser zone it was near about 2400 degrees centigrade. Okay, so with this analysis we could find out that when there is sufficient supply of air as a coolant, the temperature of the content of heat pipe was reduced by huge amount. Okay, so this is all about our today's analysis. In this analysis, we wanted to show that with same input variables with different conditions, we could see different results, right? The different results were obtained by the cooling of air. Okay, thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.